Welcome to part one of a two-part series on photoelectron spectroscopy. Photoelectron spectroscopy is a very powerful experimental tool that allows us to verify our models of electrons. Before we get into it too much, I want to remind you of Bohr diagrams. This is a Bohr diagram for a neon atom, and we know that neon is number 10 on the periodic table. That means it's got 10 protons, and so there are 10 protons in the nucleus, and there are 10 electrons. 2 of them are in the first energy level, represented by the 2 red dots here, and 8 of them are in the second energy level, and those are represented by 8 dots. So a total of 10 red dots. Those are the 10 electrons to represent neon. Now, photoelectron spectroscopy is an experimental technique that allows us to see that this model, this Bohr diagram, is accurate. We're onto something here. An electron configuration is another way of representing the electrons, and we have worked on a lot of electron configurations, and so it's no surprise to you that the electron configuration for neon is 1s2, 2s2, 2p6. The second energy level is right here, and inside the second energy level there are 2 sublevels, the s and the p. Now the Bohr diagram did not show the sublevels, it just shows the second energy level. But the electron configuration is more explicit. It shows them, it says, hey, 2 electrons here, 6 electrons here, total still 8. And the total in the first energy level, there's 2 electrons. Now, what experimental evidence do we have that there are 2 distinct sublevels inside of the second energy level? And furthermore, how do we know that there is one of them, the p, has triple the number of electrons as the other one, the s? Well, photoelectron spectroscopy gives us the experimental evidence that both of these models, the Bohr diagram and the electron configuration model, both of them are accurate. It lends evidence that these models are valid. And so today, we're going to learn about photoelectron spectroscopy, and there are 2 things that you should have a good handle on. The first, by the time this video is over, if I've done my job, you should be able to explain the photoelectric effect. You may not know what it is now, but in just a couple minutes you will. The second thing you should be able to do is to describe a PES, or a photoelectron spectroscopy experimental setup. What does the experimental setup look like? What does it look like when somebody is conducting photoelectron spectroscopy in the lab? So, in just a few short minutes, you'll be able to explain the photoelectric effect and describe a setup. Okay, well, to understand the photoelectric effect, we're going to think about a bike for a minute. And let's say we've got our bike, and there's a neighborhood boy. All right. And let's say you're riding the bike. And here's a neighborhood boy. He's standing off to the side, and let's say maybe he's troublesome. I'm not going to draw a smile. I'm going to draw a little her. All right, he's trouble, and he tosses a ball at you while you're riding on your bike. And it's coming right at you. Now, you may not be very worried that a boy tossed a ball at you, but what if that ball had a lot of mass? What if it was a heavy ball? And what if he really launched it? I mean, this thing is traveling with a lot of velocity, and it's coming right at you. It could theoretically have enough energy to knock you right off your bike. And I hope you fall on the grass, not the pavement. Well, just like a ball, if the ball has enough energy, it could knock somebody off a bike. That is an analogy for what's called the photoelectron effect. Let's bring back our Bohr diagram here. And let's say we've got, what the photoelectric effect is we've got, let's see. All right, we've got energy coming in. This is electromagnetic radiation or light waves. Could be ultraviolet light or even X-rays. This electromagnetic radiation is coming in and we're shooting it at an atom. And if it has enough energy, it can actually cause one of these electrons to get ejected. This electron, for example, could get ejected, knocked right out of orbit. So again, the photoelectric effect is if you have a photon, photon is a fancy word for a light energy packet. If a photon of light or ultraviolet photon or an X-ray photon has enough energy, it can kick an electron out of the orbit, and that's the photoelectric effect. Shining light on atoms can knock off the electrons, and Einstein actually won a Nobel Prize for his explanation of the photoelectric effect. All right, how does this relate? What does this tell us about atoms? Well, let's take a look at an experimental setup for photoelectron spectroscopy. Here we've got a photon source. A photon source means that this is just shooting photons, and those photons could be light, like visible light that we could see, or it could be ultraviolet light, or maybe even X-rays. Okay. And it's being shot down at a sample. What is this sample? Well, we'll just say it's a maybe a piece of metal, it looks like. And if those photons, the UV or X-ray or visible light, if those photons have enough energy, electrons are ejected from the metal. Okay. And if those electrons are ejected from the metal, then they will enter into this energy analyzer. It'll go like this. Now the energy analyzer is a little complex, but there's an electric field in there, and it measures, this is the detector right here, so we've got a detector. And it measures the amount of energy that the electron has. Now the detector is connected to a computer, like that. And so this is based on the photoelectric effect. We know the photoelectric effect is that if electromagnetic radiation, if the photons from electromagnetic radiation have enough energy, they are able to knock an electron out of an atom. We can then analyze the energy that that electron has, and the computer will spit out a graph for us. The graph that the computer gives us is very important. And in the next video series or video lesson, we're going to look at what that graph tells us. And we're going to specifically learn how the spectrum or the graph of the energy of electrons verifies our Bohr diagrams and our electron configuration models. So if I've done my job, that means that you can now explain the photoelectric effect, and you also can describe a photoelectron spectroscopy experimental setup.